Let's look back at a problem from the very start of the semester. A car at position 60 meters from the nearest stop sign, or from the most recent stop sign, is going 11 meters per second, and it's decelerating at 7 meters per second squared, which is pretty hard stomping on the brakes, trying to come to a stop before it hits a kid that's on a bike at 65 meters. So knowing what you know now about antiderivatives, try to solve this problem. Spend a few minutes on it and come back to the video. Okay, welcome back. What do we know? Well, we know the acceleration, and I guess we'll presume that that's constant. We want to know how the velocity is changing with time. We want to know how the position is changing with time. So what we can say the acceleration at time t is negative 7 meters per second squared. The deceleration means the acceleration is negative. So while the car is moving this way, the acceleration is kind of trying to pull it back that way. What else do we know about acceleration and velocity? Well, we know that acceleration is the derivative of velocity, and we want to know the velocity, and we know the acceleration, so we need to kind of undo the derivative, right? So we could say that the velocity is the antiderivative of the acceleration, and that's integral of negative 7 dt. And what's the integral of negative 7? It's negative 7t plus c. But here's the problem, we don't know what c is. Can we figure it out? Well, what's going on here? At time 0, when the whole thing starts, the car is going 11 meters per second. So we can say that we know v at time 0 is 11. So v at time 0 is 11, which is negative 7 times 0 plus c. So this 0 is becoming our t there. And solve for c. Actually, there isn't much solving to do. You just get 11 equals 0 plus c. So you get c equals 11. So we know v of t is negative 7t plus 11. And that tells us what the velocity is, but it doesn't tell us what the position is. We need to know how far are we going to go by any particular time t. So at this point, now that you've seen me do this, try to say what are we going to do next to get the position. So we know that velocity is the derivative of position. Position is traditionally written with an s. I'm not sure exactly why. So can we do the same thing we just did? Say position at time t. If velocity is the derivative of position, so position is the antiderivative of velocity. dt. And then what is my velocity function? It's negative 7t plus 11 dt. So go ahead and take the antiderivative of that. I mean, this is saying, in some sense, take the antiderivative of that. So we get negative 7 times 1/2 t squared plus 11t plus, well, it's tempting to write c here, but I already have a c in the problem, and we figured out that it was 11. So I'm going to write something else here. How about d? That's another good constant. What can we do to figure out d? Well, what do we know about s? We know that at time 0, s is 60. S at time 0 is 60. So we can say s at time 0 is 60, which is negative 7 times 1/2 t squared plus 11t plus d, except these t's are zeros. So we're saying 60 equals 0 plus 0 plus d, or d equals 60. So altogether we've got s of t equals negative 7 times 1/2 t squared plus 11t plus 60. Let's check units on that. -7 is meters per second squared. 1/2 is unitless, and t squared is seconds squared. 11 is meters per second. T is in seconds. 60, well, the 60 was originally meters along the road, so that's also meters. So seconds squared cancel seconds squared, we get meters. Seconds cancel seconds, we get meters. So altogether the units are meters, so that's good. So now we can go plot the velocity function. The velocity is a function of time, and position is a function of time. So let's do that. All right, I've already typed in v of t equals -7t plus c, but we'll kind of recreate what we went through. We don't know what c is yet, so we'll add a slider for it. I happen to know we're going to need it to be bigger than 10, so let's let it go up to 20. And we know that the velocity at time 0 was 11, so I want my my velocity curve to go through that point, and I could slide this slider until it goes through that point, and that's not a bad idea. Another way to see it is, instead of sliding a slider to make it go through a point, you could say, back when I said v of t equals -7t plus c, that could be true for any c, so I could put in a whole range of stuff here, like -10, -8, dot, 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 up to, let's say, 15. And we're saying all of those curves work for giving us the acceleration we need of -7. So we're kind of trying to select the one of them that goes through that point. Obviously we needed a few more curves there. So we need the one that goes through that point, which did end up being c equals 11. So that was for velocity. And then for position, we said position at time t was -7 times 1/2 t squared plus 11t plus d. We can make a slider for d. We know we should be operating up in the range of like 60 meters, so we'll do that. I'll change this color to something else. And give ourselves some more room there. And then we know that the position at time 0 was 60. So I want to slide my d slider here until it goes through that point. And that's kind of hard to judge. I mean, we know from the algebra we did paper and pencil that that's right. But again, another way of thinking of it is d could have been any value like -10, -5, dot, 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 up through 100 even. And we're trying to pick the one of those curves that goes through the point that we know the position function should go through. So again, that did end up being 60. And then we wanted to say, does the position ever get to 65, or when does it get to 65? So we could just plot y equals 65. And apparently the car does get to time 65, to position 65 by time 0.5512 seconds. And at that point, it's still going 7.192 miles per hour, meters per second, which is still pretty fast. So it better be stepping on the brakes even harder if it's going to stop by the time it gets to the bike.